Okay. So previous most significant bit will be copied in the present most significant bit. Okay. This is what arithmetic shift. What is the difference here means, in case of logical shift, irrespective of the previous most significant bit, newly added MSB is always 0. Okay. It means when we go by logical shifts means it assumes that the numbers are unsigned, then there is no matter of sign. Most significant bit is not considered as a sign, then you can add a 0 always. Okay. But for signed numbers, MSB represent the sign of it, right? When we shift the number, shifting a number is nothing but multiplying by 2 or dividing by 2. Okay. For right side shift, it is dividing by 2. The sign component will not be changed. It should not be changed. So whatever it is the most significant bit, that we will keep as it is, and again it is participating in shift operation. Okay. That will preserve the sign of the number. That is the main advantage in arithmetic shift. Okay. In case of 2's complement representation, you should follow this rule because most significant bit is also treated as if like magnitude bit, and we are operating on those bits in case of 2's complement operations. Okay. So if it is representing sign, then for right shifting you have to follow arithmetic right shift only. Otherwise it will update the number. A negative number may become a positive if you don't use arithmetic shift. That will cause wrong result. Okay, right? So the here a shift is arithmetic shift, right? Because the registers involves the sign bit. AC and QR, they include the sign bit, right? After one inspection of the least significant bit of the multiplier, we will decrease the sequence counter by 1 and it repeated until it becomes 0. Okay. So this is about algorithm, and let us see the example. What is base for Booth's multiplication algorithm is any number which is having a series of ones start from 2 power m to 2 power k, we can represent that number as 2 power k plus 1 minus 2 power m. Okay. Any number, 2's complement number, any number can be represented in this way. When such number is multiplied by m, okay, so the multiplicand is enough to shift left side by the power of m, and the same multiplicand is shift left side by the power of k plus 1, and they were added the together or subtracted to get your corresponding product. Okay. So this base is used for Booth algorithm, right? Let us see the example on this. So we'll do directly rather than direct observation. So take any two numbers. You tell me any two numbers. Multiplicand. Tell me any two numbers.
25 and minus 16, ma'am.
Minus 16 multiplier.
25.
25. Okay. So multiplicand is
ma'am,
minus 16. Yes.
Ma'am, we are able to see only the PowerPoint window, ma'am.
Okay. Is it okay?
Yes, ma'am.
So multiplicand is minus 16, multiplier is 25. So we have to convert this to binary, right? Minus 16 in binary. So first you have to take plus 16, 0, 1, 0, 0, 0, 0, right? This is plus 16. And to get minus 16, I have to take 2's complement. 1, 0, 1, 1, 1, 1, plus 1, right? 1, 1, 0, 0, 0, 0, 4 zeros. So this is multiplicand, right? And coming to multiplier, it is 25. 25 in binary.
11001, ma'am.
It is 25. So number is positive. Plus 25. 0.
1101.
1, 0, 0, 1.
Yeah, yes, ma'am.
16 plus 8 plus 1. 24, 25. Right? So this is multiplier. So we have three registers totally: accumulator, BR, and QR. Okay. So what should we load in accumulator?
0.
This is the final product, right? So all zeros. How many number of zeros? Number of zeros in your whichever is greater in that way. Okay. So here 6 bits are there. Anyway, here also 6 bits. So I can take 6 bits in my accumulator. And the BR register multiplicand should store in a BR register, which is nothing but minus 16. That is 1, 1, 0, 0, 0, 0. BR is 1, 1, 4 zeros. And in QR register, I have to load multiplier plus 25. So which is nothing but 0, 1, 1, 0, 0, 1. What are the other things? Sequence counter. How about sequence counter? How many number of bits in multiplier? 6 bits. So sequence counter is 6. Right? These are sufficient. Now I have to proceed for the algorithm. Before that, I need to assume that previously shifted out bit, which is 0 initially. Okay. Right. So now consider it. I'm taking a table, one for observing Qn and Qn plus 1, whether it is 1, 0, 0, 1 or 0, 0, 1, 1. After that, one for BR, the operation, whether it is addition or there, and accumulator followed by QR register, followed by Qn plus 1 and the sequence counter. Okay. Right? So we need to inspect the bits Qn and Qn plus 1, and I require a BR. After that, AC and QR, and then least significant bit Qn plus 1, because whatever it is the bit that is shifted out of QR should be loaded in Qn plus 1, and finally the sequence counter. Now tell me the initial values. BR is the multiplicand, which is 1, 1, 0, 0, 0, 4 zeros. And you may require to add BR or subtract BR from partial product, which is stored initially in the accumulator, right? So to subtract BR, I have to calculate 2's complement of BR and add it to accumulator, right? So for that, I am I want to take BR bar plus 1. This gives us the minus BR value, okay? So which is nothing but minus BR value, right? So which is BR is minus 16. So minus BR is plus 16. The value is 0, 1, 0, 0, 0, 0. Right? This is plus 16 and this is minus 16. Coming to accumulator, initially partial product is all zeros. QR holds the multiplier 0, 1, 1, 0, 0, 1. And Qn plus 1 initially 0, sequence counter is 6. Okay. Right. So now you have to inspect Qn plus 1. This is what Qn and Qn plus 1. See, right? So Qn is 1 and Qn plus 1 is 0. Right? So now we are inspecting the present significant, least significant bit and the previously shifted out bit, initially which was 0. Now the combination is 1, 0. So if it is 1, 0, what should we do?
Subtract.
We will be getting m term, right? So series of ones start from here. So I'll be getting m term. M terms are subtracted. So I have to subtract BR. Okay, BR need to be subtracted from AC. Right? The operation is subtracted. So you have to add minus BR to AC, which is nothing but 0, 1, 0, 0, 0. Am I clear?
Yes, ma'am.
So after doing this, I'll be getting the result anyway, the same initially, which is 0, and your QR is again 0, 0, 1, 0, 0, 1. Okay. Right. So this is one operation is performed. After that, what you have to do? Arithmetic shift right. Arithmetic shift right. Right. You need to shift arithmetically AC and QR. Most significant bit here is 0. So the same bit is copied and then again participating, the same bit is participated in a right shift. Okay. So 0, 1, 0, 0, 0. And this 0 will be placed in QR register 0, 0, 1, 1, 0, 0. And now the least significant bit is shifted and placed in Q1 plus 1. So one operation is over. The sequence counter is decreased by 1. So I'll be getting 5. So with this, we have completed one cycle, first cycle, right? Is that clear?
Yes, ma'am.
In case of arithmetic shift, the most significant bit is copied directly as new MSB and the same MSB is participated in shift operation also. Okay, this is how right shift is happened. Okay, so likewise this we got here, right? This is the arithmetic shift. Next, second cycle. Now what is Qn?
0.
0. Qn plus 1?
1.
1.
1. Okay. So now the combination is 0, 1. What is the operation?
Addition.
Addition. You have to add BR to AC. What is BR? BR is 1, 1, 0, 0, 0, 0. Okay. So this thing you have to do. This is now the previous accumulated product, and this you have to add. So after doing this, I'll be getting simple, no carries are involved here. This is the result, right? And your QR is as it is 0, 0, 1, 1, 0, 0. Okay. After addition, what you have to do? Again, arithmetic shift right. So in arithmetic shift right, the most significant bit is 1 here. So newly added MSB is equal to previous MSB, that is equal to 1. 1, 1, 1, 0, 0, and 0, 0, 0. Sorry. 1, 1, 0, and 0. Okay. Arithmetic shift right happened and sequence counter decreased by 1. Right. This completes the second cycle. For next cycle, now what is Qn?
0.
Qn is this value, right? Qn is 0 and Qn plus 1 is also 0. So what operation you have to do?
Arithmetic shift right.
Only arithmetic shift right. No operation of addition or subtraction should not perform. Only arithmetic shift right. Right? So this is 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, 1, 1, 0. After shift, decrease the sequence counter by 1. Right? Since 3, it is not at 0, proceed further. What is Qn now?
1.
1. Qn plus 1?
0.
0. Operation is subtract.
Subtraction.
So you have to add minus BR, which is nothing but 0, 1, 0, 0, 0, 0. So after adding, how much is this?
1 carry. 0, 0, 1, 1, 1, 0.
1 is carry, that is extra bit. For 2's complement addition, anyway, we will neglect it. 0, 0, 1, 1, 1, 0. Am I right?
Yes, ma'am.
Yes, ma'am.
Okay. This is subtraction is happened, and your Q is same 0, 0, 0, 0, 1, 1. Now you have to perform arithmetic shift right. Now most significant bit is 0, so newly added bit is also 0. 0, 0, 1, 1, 1, 0, 0, 0, 0, 0, 1. 1. SE is 2. Right? This completes the next cycle. 1, 2, 3, 4. 4 cycles are finished. Next. What is Qn?
1.
1. Qn plus 1 is 1.
1.
So operation only arithmetic shift right. So 0, 0, 0, 0, 1, 1, 1, 0, 0, 0, 0, 0, 1. Right? SC 1 not at 0. So next cycle. Now present Qn is 0.
0.
Previous Qn 1. So 0, 1 operation is addition.
Addition.
You have to add minus BR. So minus BR, sorry, BR. 1, 1, 0, 0, 0. So which is 1, 1, 0, 0, 1, 1. And this 1, 0, 0, 0, 0. Is next. What you have to do? Arithmetic shift right. Arithmetic. So 1, 1, 1, 0, 0, 1, 1, 1. 4 zeros, and this is 0. Right? And SC becomes 0. Algorithm is finished because the sequence counter is 0. You check. This is your Qn plus 1 values. And if you check your QR, this is your multiplier and sequence counter. So what is your final product? Your final product is in A and Q registers. This is what your final product. Okay. So final product is 1, 1, 1, 0, 0, 1, 1, 1, 0, 0, 0, 0. Right? So by observing the most significant bit, it is clear that the result is negative. Okay. So to get its corresponding decimal value, I have to do by 2's complement, right? 0, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, 1. Then add 1 to 8. So 0, 0, 0, 1, 1, 0, 0, 1 0 0 0 0, right? So what is this value? This 2 power 4, 2 power 7, 2 power 8. So 256 plus 128 plus 16. How much is this? In decimal, it is 400. Am I right?
Yes, ma'am.
400. Since we got this 400 after 2's complement, so the actual product is minus 400. Okay, 16 into 25 is 400.
Yes, ma'am.
16 into 25 is minus 400, right? This is minus 16 into plus 25 is minus 400. That is how we have to perform Booth's algorithm. Okay, this is what the procedure that we wish to implement in a company. Is this clear? Example?
Yes, ma'am.
Okay. Anybody have other doubts? Any other doubts? See, while performing addition, right? While performing addition, if you get any carries, okay, you have to neglect because we are dealing with the 2's complement, right? You have to neglect. So hence we don't have any extra bit like E, which was there in sign magnitude multiplication. Okay. Right. Next topic is division. Okay. So now how we perform division, first of all, division algorithms. Next, how we perform division with help of pen and paper. The terms here are dividend, divisor, or the
Quotient.
inputs. Results are quotient and remainder.
Reminder.
Right? Okay. Let us take a simple division example. Let us consider numbers. Dividend. Usually, since we are performing dividend by divisor, right? When we perform dividend by divisor, obviously the dividend should be greater than divisor. That is the primary condition. Otherwise, you cannot perform the division, right? Am I clear? So, in case of our normal decimal division, okay, some decimal division maybe some 293. I want to divide it by some maybe 14. Okay. So then what you have to do? First, you have to check the number of digits here 2. So I will take only 2 here and check whether how many times my divisor can be divisible, subtracted from the dividend. Okay. So if I go by 1, 14 or 2, 14 2s are 28. Okay. Or 3, likewise 14 3s are 42. Okay, which is bigger than the dividend, first 2 digits. Okay, so 2 is sufficient. You have to check this figure, how many times that the dividend can be gone from a divisor, right? And we'll be getting 1, which we call this as partial remainder, not yet completed division. So hence this is called a partial remainder. And we'll take the next digit 3 and we proceed further. Okay, right? So how many times it is going? 0 times. Okay. I'll be getting the total remainder as 13. Right?
Yes, ma'am.
This is what your remainder and this is your quotient. Okay. In case of decimal, you have to check how many times my divisor can go from dividend, because I have 9 possible cases. 1 time, 2 time, 3 times, 4 times, till 9 times. Okay. But in case of binary, since we want to implement the same division in computer, in binary it is very simple. Either it is 0 times of the divisor or else 1 time of the divisor. That's all. There is no possible other conditions. Okay. So binary division is very simple than decimal. Here multiple cases you have to check this condition. Okay. So if you go for by binary division in the same way, right? So consider 293 in case of decimal. How much is that? 273. Sorry, 293. In decimal is binary is 1001 00101. Nothing more 125. Okay, so this is 293. Divided. Coming to divisor 14, it is 0, 1110. Okay, we are not dealing with sign right now. Let us take about the magnitudes only. Okay, right? So how we can perform the division in case of binary? 100100101 is the dividend, and we are going with divisor. Divisor are 4 digits. Here also we will consider first 4 digits. Okay. So I will take only first 4 digits. Since the first 4 digits are, which is nothing but 9, and here it is 14, which is lesser than the first 4 digits of my divisor. So I will take extra 1 more digit. Right? So total 5 digits. Now I will check. Since now the number, this number is now 16 plus 2, which is 18, and this is 14. So this number is greater than this number. So hence I can go by start with my quotient with 1. Okay. How to write my divisor here? It should start from leftmost bit. Okay. So from here I have to write. So my divisor has to be shifted right side by 1, and then it has to perform the subtraction. Am I clear? Okay.
Yes, ma'am.
So here my divisor has to be shifted right side by 1, and then the subtraction has to be carried out. Okay. Now perform the subtraction. 0, 0, 0 minus 1. We cannot perform, so I have to take borrow from here. There is no borrow here, so I need to take it from here. So here I'll be getting 1, and here it is 2. 2 minus 1, 1, 1 minus 1, 0. Okay. We got 4 as a partial remainder, right? Now I have to continue from here. This is 4 and my divisor is 14. So this is bigger than this, right? So I have to take extra one more 0. And what is this? It is 8, which is still bigger than this. So what should I do? I need to make my quotient as 0, because 0 times it will go in this, and then take this number. Now it is 16 plus 1, 15. It can go by 1 time. Okay. And this number has to start from here. 0, 1, 1, 1, 1. And perform the subtraction. The result is 1 minus 0, 1. And here we have to get a carry from here. I'll be getting 1 here, 1 here, and 2 here. 2 minus 1, 0. 1 minus 1, 0. 1 minus 1, 0. Okay. Two minus 1, 1. అది వేయాలి కదా నేను. I have reached 1. 1 minus 0, 1 వేసాను. ఆ తర్వాత 2 minus 1, 1 should be there. After that 0, 0. And then here we have one more term. Did I miss anything? No, this is 0, right? Nothing is there here. 0 here. 3 ones only, no? 14. 3 ones and 0. Am I correct? Are you following me?
Yeah, ma'am.
16 plus 1, 17. 17 minus 14, 3. Correct. Right? And this is 3. So after this, I have to take this
Yes, ma'am.
0 here. And still it is 6. So I have to add one more 0 times only. This 14 can go, and take this one more 1. Okay. And this is 1, 2, 3, 4. 4. How much is this?
13, ma'am.
13. Still it is lesser than this. So you have to stop. It is going by 0th time only. And I have to take this as my remainder, which is 30. And what about this value? 2 power 0, 2 power 1, 2 power 2, 4. 3 to power 4, 16. How much I got? 20. Okay. 16 plus 4, 20. 20 is the quotient, 13 is the remainder. So while doing this, what are the observations? The number of digits in your multiplier and divisor, and the number of digits in your dividend. Obviously, it should be more. First condition is your dividend should be greater than divisor. Okay. If initially the dividend is lesser than divisor, you can say that the division is not possible. Okay. Right. We won't proceed for the division. If it is so, then 0th is the quotient. Whatever is there in the divisor, that itself gives you the remainder. Okay. Right. That is first condition. And second condition, how many number of bits are there in your divisor? That many number of bits I will take it from the dividend. Okay. How many times it is gone? That has to be checked. If it is first time, if this number is lesser than the divisor, then what should I do? I have to take the next digit also. Okay. So now I have to take like this. I have to take the next digit. 5 digits I need to take, and take one time of your division. How the divisor has to be placed? It has to be placed right shift by one bit, so that the bit to bit alignment will happen. Okay. So the divisor has to be shifted right side by left, and then it has to perform the division. Okay. After performing the subtraction, you need to take the next digit and again check how many times it is going. If this portion, the partial remainder is greater, then you can go by quotient value either 0 or 1. If the partial remainder is greater, obviously the quotient will be 1. If it is lesser, then I have to take one more bit from the dividend. And your quotient have to be now shifted right side. How many number of bits that we are taking extra, that many number of bits it has to be shifted. And then perform the subtraction. Proceed. Go on. Okay. Right. So while implementing algorithm, you are doing this. So manually you can calculate this is 9 and this is 14. So first 4 digits are not sufficient. So hence I am taking one more digit so that it will become now as 18. Okay. Likewise you are doing. Okay. But how the computer knows that the first number 4 digits of my dividend or whether they are greater or lesser? It doesn't know until unless it has subtracted. Okay. So initially it will take one time of the divisor and it will take 1110 and perform the subtraction, right? So if the subtracted result is negative, it means that the previous dividend which we have taken, it is lesser than the divisor. So I have to take one more digit of it and shift the divisor right side by left and then perform the subtraction. That is the procedure you have to do. Am I clear?
Yes, ma'am.
Okay. See, we are doing manually, so we know how many number of bits from your dividend has to be taken initially, right? Manually we can calculate the number and we can do, but with respect to computer, you need to perform first the division. Okay. So it will know only first 4 digits it has to take because the number is divisor number is 4 digits 110. What it will do, it has to do one time and then 1110. It need to subtract. This is 1. We cannot do subtraction, so take a borrow from here. This is 1 and this is 2. 2 minus 1 is 1. 1 minus 1 0, and this is gone, so it is changed to 0. 0 minus 1 you cannot do, so you need a borrow from other thing, and we'll be getting 2. 2 minus 1 is 1. So this we'll be getting, and we require a borrow to do subtraction. So hence the computer recognizes that the dividend of first 4 digits is lesser. So it has to take the next 4 digits. So this is wrong and it needs to take the first 4 digits. Okay. Right. So since after performing this only, then the computer can recognize that the first 4 digits are not sufficient. It has to take 5 digits. Okay. So but after, since it has been already done subtraction, right, the partial remainder is replaced here in the previous register. The partial remainder will be replaced. Okay. So you need to restore the dividend back. Okay. How can we restore the dividend back? By adding again the divisor to this. If I add the same divisor again, I can get my previous dividend, which is 0001. Okay. So this procedure have to be done repeatedly to know whether it is one time or 0 at the times it is going, the divisor is going from the dividend. Okay. So you need to restore the dividend. So hence this algorithm is said to be restoring division algorithm. Okay. There are even non-restoring method that we'll see later. So right now we are seeing division restoring algorithm. Okay. Every time, first one time the divisor will be subtracted from the dividend and it will check whether the result is negative or positive. If the result is negative, then you need to restore the dividend and then take one more extra bit. How can you take one more extra bit? See, I'll be getting after restoring. This is the result that I got. Okay, I have to take one more extra bit. So now 5 digits, and then now again try it with the Q and quotient first digit as 1, and you need to write your divisor as shifted right side by 1 bit and then right. Okay, because 5 bits are my now dividend. You need to shift right side the divisor by 1 bit and then right. Okay. So here, rather than shifting right side the divisor by 1 bit, I will shift the dividend by 1 bit in left side, and then I will write my divider. Okay, so I will write my divisor so that they will be in a compatible positions. Okay, so rather than shifting the divisor by right side, I will shift the dividend by right side, because in while shifting, see, the most significant bits which were already participated in the division, those bits I don't require further. So hence I will remove them from my register by shifting it to left side, so that I can accommodate the same register for my final remainder. Okay, so that is what the advantage that is coming while shifting the dividend or partial remainder left side rather than shifting the divisor right side. Okay, and this procedure has to be continued till you end the total number of bits in your dividend. Okay, so we'll see the algorithm now. Division algorithm. So this is how the division is happening, and this is the dividend, and this is divisor, right? So your dividend is in A, quotient will be in Q, B register which holds the divisor. Okay, only the thing here is always the length of the dividend is assumed to be twice the length of divisor. That is the basic condition, so that I can confirm that my dividend is greater than divisor. Of course, there are situations even with all zeros, the dividend can be lesser than divisor. That can also be treated in this algorithm. Okay, since here we have 5 bits, so first 5 bits are considered. Okay, since my A here it is just 14, but here it is 16 plus 2 plus 1, 17, bigger. Okay, first 5 bits of A is lesser than B, right? So first 5 bits of A is lesser than B, so I have to take 6 bits, 6 bits of A. Okay, now I have taken 6 bits. See, if I take first 5 bits, these are lesser than B, so I am taking first 6 bits, right? And I will made my quotient 1 initially at the 6th position. My initial quotient is 1 time my B need to be subtracted. How you have to write B? That has to be shifted right side by 1, so that the bit to bit alignment will be same. And then I'll perform the subtraction. So this is what the result we got. Okay, 0 1 0 1 1 0. Right? And next till here, this is what your result, and I will take the next bit 0. Okay, so these are the bits which is greater than B here, so hence again my quotient is 1, and then I am performing the subtraction. This is the partial remainder. Again take the next bit, and this one is lesser than B, so I will make my present quotient as 0 bit and take the next bit. Okay, so this number is now greater than or equal to B. Now it can go by 1 time and then perform the subtraction and get the next bit 0. Okay. So this is lesser than B, so it can go only by 0 at the time. So my B, 0 times of B is 0. I'll be getting the final remainder as 3. Okay. This is how the division is carried out in binary with these numbers, right? Hardware implementation, when we come for hardware implementation, when the division is implemented in digital computer, it need to be some changes to make it convenient. So first change, instead of shifting the divisor to right, the dividend or the partial remainder, okay, is shifted left side, thus leaving the two numbers in the required relative position. Okay. So we will shift the dividend to left side so that already considered bits in the division process can be eliminated. Okay, that is one advantage. So they both will be at the required relative position for doing the subtraction. This is first change. And second change, subtraction may be achieved by adding 2's complement of B to A. Okay, so how can I perform subtraction in computer? I will add 2's complement of the divisor to accumulator so that subtraction can be carried out. Okay, so whatever it is, the information that is getting from the end carry, that gives you the magnitude relation between the divisor or dividend and the partial remainder. Okay, so the relation between the dividend or the partial remainder and the divisor is explained by the end carry E, because the subtraction is carried out by 2's complement addition in your computer. So if you get E as 0, it means the dividend or partial remainder is lesser than the divisor. So you need to make my quotient bit 0 and then take one more extra bit. How can I take one more extra bit? By shifting the dividend to left side one bit. So previous most significant bit we can lose and the present LS can be considered in the same 5-bit alignment. Okay. So likewise from the end carry, I can conclude the magnitude comparison, right? So this is how the hardware implemented in sign magnitude data, BS, AS, QS. Okay. So Q register holds the divisor. Okay. So A and Q registers holds the dividend. Sorry. Where I said the dividend is of twice the length and the divisor is of n length, n bit length. Okay. So B register holds the divisor and A and Q register holds the dividend. Okay. If it is a 5-bit length, 5-bit magnitude length, then A and Q, these two are also 5-bit magnitude length. Most significant 5 bits of the dividend are copied in A register. Least significant 5 bits of the dividend are copied in a Q register. Okay. So totally 10-bit length AQ register forms the dividend and divisor will be in B register. Right. Okay. So here first 5 bits of it and first 5 bits of A register, most significant 5 bits, they both perform the subtraction. Okay. So after performing the subtraction, if the end carry E is 0, it means my dividend is lesser than B. So my dividend is lesser than B, right? So what should I do? Because it is lesser than B, I need to take one more extra bit of this dividend, the subsequent bit. Okay. So that makes the rightmost bit as 0. The present 0 times it has gone. Okay. It will take the next 6 bits and again perform the subtraction. If E bit is 1, it means the result is positive. So the QN value can be fixed. One time it is correct. Okay. If the result is negative, it means The Qn is not 1 right now. It is 0 time. It is 0 time because the subtraction cannot be done because A is lesser than B, right? I need to restore A because here after performing subtraction A minus B, result is saved back to A. If your end carry is 1, it means A less than B. You should not do subtraction. So I have to restore back my result, my register contents. So by adding again a B to the subtracted value, I'll restore my dividend and I'll make my Qn bit 0 and proceed further. Okay. So this is how the division is carried out. We'll see the flow chart that makes little clear. See, this is divide operation. Dividend will be in AQ register. Leave about the sign component. Sign bits are available in Q, AS and BS. Anyway. Okay. Divisor is in B. And your sequence counter is n minus 1 because total number of bits including the sign bit n length. So number of magnitude bits are n minus 1. So SC is n minus 1. First, initially, I'll perform the subtraction A minus B by considering first 5 bits. If E is equal to 1, it means A is greater than B. Okay. If E is equal to 1, A is greater than B. Initially itself A is greater than B. Obviously, I will be getting a result which is greater than number of bits dedicated for storing my quotient. Okay. See how many number of bits after doing this finally. A register holds the remainder because the partial subtracted result is available in A. So finally my remainder is in A and the quotient bits, least significant bits, we are updating either it is 1 or 0 based on the subtraction. So quotient is in Q register. Okay. So your quotient should be not greater than n bits for n minus 1 bits, which is nothing but 5 bits for the previous example. Okay. See, initially itself the quotient is 1. It means obviously the double the length is there for AQ register. The quotient will be greater than 5 bits or greater than the number of bits dedicated to fit in this register. That's what called addition overflow. Division overflow flag will occur. So it is A much greater than B. So hence you cannot perform division. Right? It is infinite. Quotient is infinite indirectly, which we are unable to fit into the specified 5 bits. So hence divide overflow. See example, for example, I have 8-bit register for A and 8-bit register for Q and again another 8-bit register for B. Okay. So let us suppose I want to perform division of a number with take 8 bits means 2 to power 0 to power 7, 128 by, this is a divisor and quotient let it be double the length, right? 16-bit length. Okay. Quotient, consider this as to have larger division. (16 by 256). 16 by 16. 16 are 16. So which we can store. The remainder is 0. Okay. Let us suppose if my result is if my dividend, let us consider 1256. Okay. 1256 by 16. How much is this? Sorry. 1256 by 16. I'll be getting 78. Even here also 2 digits, this 2 digits. It can even go. 255 by 2. 128. Okay. See, this is what simple example I want you to tell. So let us take only 2 digits. 2 bits are there for my input. 2-bit registers. Simple case. I am performing division with the 2. 256. Okay. Which result is 128. Okay. Right. So here I could by 2, it can be maximum 2 digits. So 2 digits maximum 4, right? 4, 4, 16, right? 69, let us take. So how can I represent 60? 1, 0, 0, 0. By 2 is 1, 0. Okay. So what is the result? 8. 8 is nothing but
130.
okay, so 5 zeros, right? So I am not getting correct example to tell you where the overflow occurs. This is 8, right? This is 2. 8 by 2 is 4. How can you represent 4? 1, 0, 0. 3 digits we got, right? Okay. See, my divisor is 2-bit length. So my dividend can be twice the length of it. So 4 bits. So it is a proper dividend and proper divisor. Okay. But after when we divide, I'll be getting a divisor which is 3-digit length. But I am reserving only 2-bit length register for storing my divisor. But my divisor is having 3 digits. So I can say that it is overflow. A division overflow occur. My dividend is very much greater than my divisor. So I cannot perform overflow. It is just nothing but infinite. Division overflow or my quotient is infinite indirectly. Whichever is the value that we are unable to fit into the specified length of the register, that value will be considered as infinite. Okay. I cannot fit my available result, which is nothing but the quotient, into the specified length register, then the result is infinite. There is overflow error occurred, division overflow occurred. Similar to by 0 condition, Amma. Even if your B is also 0, it is the quotient is infinite, you can't fit the value into the given specified length register. So this is the case where overflow occurred. Okay. And we'll stop the division by indicating the erroneous flag, division overflow flag. If it is 0, then I can have that. Now there is a possibility of having your quotient can be fit into the specified length register. Then we proceed for actual division. Okay. So our time is up anyway. We'll see this in next class, right? So please wait. Let me collect the attendance. Five, 67 absent, 69 absent, 74, 79, 82, 85, 102, 104, 107, 108, 110, 111, 115, 120. 120 not there. Every time he is absent. 312. Absentees are 67, 69, 74, 79, 82, 85, 102, 104, 107, 108, 110, 111, 115, 120, 312. Okay. See, any other doubts and remaining things can be clarified in the next class.
Thank you, ma'am.
Bye for today.